In thermal energy transfer slash calorimetry problems, you're now dealing with both the system and the surroundings, rather than in the last problem here, you just talked about the system, in this case, gaining heat, gaining energy without describing anything about the surroundings. Of course, most reactions or experiments that we do in chemistry involve both, like submersion of a metal in a sample of water, and we notice the exchange between them. So this one incorporates both the system and the surroundings, and it gives you a better picture of this exchange in energy. So let's look at this equation. We just talked about how Q is equal to the mass times the specific heat times the change in temperature. So now you're going to incorporate this equation into this, or substitute for it. After all, heat involves the mass, the specific heat, and the temperature change in both the system and the surroundings. So this becomes, if we substitute for Q, this becomes M of the system times C of the system times delta T of the system. Let's make this bigger. Equals negative M of the surroundings times C of the surroundings times delta T of the surroundings. Now, this negative is really important because you have to determine where it goes based on what is losing the heat. Is it the surroundings or is it the system? So you would have to tell that from the problem. Even if you don't tell that, if you remember where it's at, it's going to give you the calculation correct at the end, because if you don't include this, you're not only violating the first law of thermodynamics, but you will get a negative number for, let's say, the specific heat or the mass, which is not possible. Now, these problems are associated with metal submersion in water. So they become usually like this: M of the metal times C of the metal times delta T of the metal equals negative M of, we're just going to use H2O, water, C of H2O times delta T of H2O. Once again, I did not forget that negative. The negative can be on the other side as well. So let's go over this problem. And I have a picture here. Let's bring this up a little bit. That will be helpful for us to use to represent the scenario here. So it says to you that a 32.5 gram iron rod, initially at 22 degrees Celsius. So imagine this is, I know it's not exactly a rod here, but imagine this is your iron rod, is submerged into an unknown mass of water at 63.2 degrees Celsius. So right away, you should know what's losing and what's gaining heat or energy. If the metal is at 22 degrees Celsius, and water is at 63.2 degrees Celsius, you know that the water is at a higher temperature, so it will be losing. So in this case, we say H2O is losing energy. Which is going to be negative. And of course, iron is gaining. energy, which is going to be positive. So it says to you that gives you the mass and everything all you need. It says that after you place it in this insulated container, the final temperature of the mixture upon reaching thermal equilibrium is 59.5 degrees Celsius. So they kept stirring and stirring and stirring, and let's say while those numbers are not visible, that the temperature finally reached 59.5 degrees Celsius. Now, I'm going to make it easy for you. That's it. They reach an equilibrium. The metal, the iron gained enough heat to get to this temperature. The water lost enough heat to get to that temperature. So that's your final T final for both. Keep that in mind. The water and the metal, or the iron in this case. What is the mass of the water? Specific heat of iron is this. Specific heat of water is that. So here's our equation. We set up our equation. Q of iron equals negative Q of H2O. And again, we should know why it's negative Q for H2O, because water is losing the heat. It's at a higher temperature. The iron is at a lower temperature, so it makes no sense that it's giving heat. So then we write our equation. So that would be M of iron equals C of iron times, C of iron times delta T of iron equals negative M of H2O, C of H2O times delta T of H2O. Very well. So what are we solving for here? It says to you right away, what is the mass, or it's asking you for the mass of H2O. So that is going to be X, M of H2O. So we must be given everything else. Well, let's solve for it, and then we can set up our equation to solve for M, so that we can actually find all the other terms and plug them in. So you know in math that if you need to isolate something by itself, you have to divide by what's next to it. So in this case, we have to divide each side by C of H2O, or the negative C of H2O, delta T of H2O. So the negative cancels out, and then all these terms cancel out. So you're left with M of H2O equals this. So we'll write it properly here. We're going to say M of H2O equals M, the mass of Fe, C of Fe, delta T of Fe over negative C of H2O. Of course, the negative can go on the top as well, but I'm just being consistent here. And now you plug in. So do we know the mass of iron? Yes, it's right here. $32.5 grams. Do we know the specific heat of iron? Yes. 0.45 joules per gram Celsius. Do we know the temperature change of iron? Yes. So we have, this is our initial for iron. And remember, this is going to be final for both, So it's going to be 59.5 minus 22.7 degrees Celsius divided by C of H2O is right here. So we put the negative, it's 4.184 joules grams Celsius. And the change in temperature is, once again, this is final for both. So it's 59.5 minus, we started at an initial Ti of H2O of 63.2. And yes, this is why we need the negative sign to cancel out this negative that you get from this calculation. Very well. So if we calculate this, we get 34.8 grams, and that would be the mass of water.